All right, as we said, these epoxides are relatively reactive, and generally they undergo epoxide ring opening type reactions. So for example, we've got an epoxide. In this case, we're going to make it asymmetrical. So we're going to have one position be more substituted than the other. And then we can add a nucleophile. And then when we imagine adding this nucleophile, one of two things can happen. The nucleophile can either attack at the more substituted position or the less substituted position. So on the left here, if it attacks on the more substituted position, it'll be on the more substituted position. And then if it attacks at the less substituted position, the nucleophile will be inserted onto the less substituted position. Of course, what we're talking about here is the regiochemistry of these reactions, right? So here, nucleophile, more substituted position. Here, nucleophile, the less substituted position. Let's first start talking about the nucleophile attacking the less substituted position. So this generally happens with a strong nucleophile. And remember, a good way to identify a strong nucleophile is if it has a negative charge, right? So negative charge, strong nucleophile. This is also sometimes called base catalyzed epoxide ring opening because bases are also usually strong nucleophiles. And this undergoes an SN2 mechanism, which explains both the regio and the stereochemistry of this reaction. But let's go ahead and take a closer look at it, right? So we said SN2 reaction. Remember that an SN2 reaction is a backside attack of a nucleophile where it attacks some kind of LG leaving group, right? And since it's a backside attack, the bulkiness of your R groups, right? In this case, I drew them as H's, but they could be something else, really matters, right? And if it's really bulky, it's going to block this backside attack. So let's go ahead and take a look at that and what the ramifications of this mechanism are. So we've got our asymmetrical epoxide, and then we're going to do two steps. Step one is adding some kind of strong nucleophile. Step two is adding some kind of water just for a reprotonation step. So we've got our strong nucleophile. It's going to do an SN2 reaction. So of course, it's going to attack at the less substituted position. Right. So boom, it attacks the less substituted position. And it also does a backside attack. So this will be the OH and the nucleophile will then be anti to one another. Of course, at this point, it's just an O minus. And then after that, we can have a reprotonation step with a water molecule. Right. So again, this is just showing off the proton transfer. Right. And then you can see that we get the nucleophile in the less substituted position, and then the OH and the nucleophile are anti to one another. Just another example of this. In this case, we're going to use cyanide, CN- as our nucleophile. It's going to attack at the less substituted position, and then it's going to kick this bond off onto this oxygen. So first step would be adding the sodium cyanide, and then the second step would be the water for the proton transfer, right? And then of course we have some kind of proton transfer, and we get our end product, right? So this is a good way to draw these molecules, is you can just draw the OH and the CN in the same plane of the board, and then you just copy your wedges and dashes from the left, right? So you can see that the ethyl is a wedge, and then that the methyl is a dash. And then just copy this side as well, but put them slightly above the cyanide, right? So they would go up here. And then if you wanted to draw the dash H, that would also go somewhere up there. But of course, we don't have to draw hydrogens. Again, I'm just going to draw the same exact reaction scheme. Right, we're adding our strong nucleophile. And we get the anti-addition, right, with the nucleophile and the alcohol. All right, so let's think about what these nucleophiles can be. They can be a whole bunch of different things. So you could use hydroxide, in which case you would end up with this type of product, right? Two alcohols. You can use an alkoxide, in which case you would end up with an ether and an alcohol. You can use a cyanide, as we saw before. You can use a deprotonated thiol. You can use your Grignard reagents, right? They too are strong nucleophiles, and so that's a good way to add some kind of carbon-carbon bond. You can just use hydrogen in the form of lithium aluminum hydride. So if we want to just keep one alcohol from the ether, or you can use your acetylide ions as well. To get that compound, right? So you can use all kinds of different nucleophiles to form all kinds of different reactions and products.